Welcome to part 4 of this video playlist about the preparation of alkenes. In this video I'll show you some examples of the preparation of allylic alcohols from epoxides. Both base and acid catalyzed isomerizations have been reported. Internal and terminal epoxides react however quite differently and will be treated separately. This here would be an example of base-induced ring opening of an internal epoxide. Groups which enhance the acidity of the proton removed will greatly facilitate such isomerizations. In the absence of such groups, an alternative mechanism can be alpha metallation followed by alpha elimination. The resulting carbene can then either rearrange to an allylic alkoxide or to an enolate. Sometimes also the allylic alcohols can be isomerized to enols and then to ketones. Besides the formation of ketones, epoxides may also oligomerize or just react with a nucleophile instead of isomerizing to an allylic alcohol. The acid-catalyzed ring opening of epoxides can yield the same products as base-mediated reactions. The regioselectivity of ring opening will be determined by the relative stability of the two possible cations. This here is a typical example of base-induced isomerization. Treatment of trimethyloxyrane with potassium terzbutoxide gave mainly a tertiary allylic alcohol along with a small amount of a secondary alcohol. No alkylation of the base occurred. It is remarkable that the tertiary alcohol was the main product. A more common result is the cleavage of the tertiary CO bond and formation of the secondary allyl alcohol, both under acidic or alkaline conditions. As in this example, here the isomerization was catalyzed by sodium methoxide, which, interestingly, was not alkylated by the epoxide. The reaction required 4 hours at 185 degrees Celsius and gave a mixture of a secondary allylic alcohol and a ketone. The alkylation of alcohols at oxygen by epoxides can sometimes be achieved under acidic conditions and often requires a large excess of epoxide. In the presence of very strong bases, epoxides can also be isomerized at low temperatures, as in this example. Here a mixture of LDA and potassium terzbutoxide isomerized the starting epoxide at -50 degrees Celsius to a mixture of 2 isomeric secondary allylic alcohols. The same result was obtained with the other diastereomer of the starting epoxide. No tertiary alcohol was formed. With enantiomerically pure bases, prochiral epoxides can sometimes be isomerized enantioselectively, as in this example. Unfortunately, an excess of the chiral base was required. Aluminum alkoxides are less basic than alkali alkoxides and may even act as weak Lewis acids. In this example, a structurally rather complex epoxide was isomerized regioselectively by refluxing in xylene with an excess of aluminum isopropoxide. Again, the tertiary CO bond was cleaved preferentially. This example is similar to the previous one. Again, the tertiary CO bond of the epoxide was cleaved first to yield a secondary allylic alcohol. The rearrangement of terpene-derived epoxides has been used for the manufacture of fragrances in the perfume industry. In this example, a 4-fold substituted epoxide was isomerized regioselectively by heating with titanium dioxide. The minor isomer eliminated water faster than the major isomer, what facilitated purification of the main product. The same transformation can also be brought about by a mixture of dimethylaminopyridine and methane sulfonic acid in dichloromethane at room temperature, as shown here. In this example, a very acid-sensitive carene-derived epoxide was isomerized with dilute acetic acid. Only the minor starting isomer reacted and underwent both cyclopropane and epoxide ring opening. Cyclopropanes show electronic properties similar to alkenes and can stabilize carbocations. This made the minor starting isomer more sensitive to acids than the major isomer. Not all epoxides can be rearranged cleanly. Cycloalkene oxides sometimes yield complex product mixtures upon treatment with bases, as in this example. A lower reaction temperature and some experimentation with other bases and solvents may be helpful in such situations. A practical method for the preparation of bicyclooctanol is isomerization of cyclooctene oxide with a strong base. It is assumed that C-C bond formation occurs by transannular carbene-CH insertion. With other bases in solvents, however, it was possible to convert cyclooctene oxide into the allylic alcohol in up to 70% yield. Terminal epoxides devoid of other activating groups are usually deprotonated at the oxygen-bound methylene group. Such metallated epoxides can sometimes even be trapped by electrophiles. If strong electrophiles are absent, alpha elimination will yield a carbene, which can either dimerize or isomerize to an enolate, as sketched here. These carbenes may also react with the metallating reagent and yield alkenes or enamines. I'll show you specific examples in a minute. Only when the R group is acidifying, a clean isomerization to a primary allylic alcohol is usually achievable. Otherwise, under alkaline conditions, allylic alcohols will only be formed in low yields, if at all. Acid catalysis is better suited for this transformation. Another potential side reaction of epoxide isomerizations is polymerization. For terminal epoxides, polymerization can be much faster than isomerization, as in the example shown here. The rate of polymerizations, however, strongly drops upon dilution. It may even be suppressed completely by adding more solvent. As mentioned, it can be difficult to alkylate aliphatic alcohols at oxygen with epoxides because of all the other reactions epoxides may undergo in the presence of acids or bases. This here is an example of a successful etherification of an alcohol with butene oxide, but 3 equivalents were required. Another way to prevent polymerization is by conducting the isomerization in the gas phase. Here, propylene oxide was isomerized to allyl alcohol with lithium phosphate at 275 degrees Celsius. Treatment of epichlorohydrin with a slight excess of trimethylamine led first to a quaternization and then to isomerization to an allylic alcohol. With cyanide or sodium acetylide as nucleophile, the same substitution and ring opening occurred, again because of the acidifying effect of these groups. In this example, a terminal epoxide was stirred with lithium tetramethylpiperidite for half a minute. Careful workup yielded a mixture of 2 enamines. These were formed by insertion of the intermediate carbene into the nitrogen-lithium bond of the base, followed by elimination of lithium oxide. This reaction was slightly faster than the dihydrochlorination. If a mixture of lithium tetramethylpiperidite and phenyllithium was used as base, carbene insertion occurred into the carbon-lithium bond, and a substituted styrene resulted in high yield. Other ethers are usually less reactive than epoxides and do not undergo elimination readily. Acidifying groups can, however, accelerate such reactions, as in this example. Here, lithium methoxide was eliminated from the starting ether, and a second lithiation gave a stabilized allylic carbanion which could be trapped with propione aldehyde. In this example, naphthoxide was eliminated and propene obtained by heating the starting ether with a 2% of an iridium complex for 2 days. THF is a fantastic solvent for polar organometallics, but unfortunately it can be metallated and undergo fragmentation. In this example, 2-phenyl-THF was refluxed in ether with just 1 equivalent of propyl lithium. After hydrolysis, mostly acetophenone was obtained. This reaction probably proceeded by lithiation and fragmentation into a lithium enolate and ethylene. Also, unsubstituted THF undergoes this kind of reaction with lithiated alkanes upon warming. Alternatively, THF can be cleaved with polar organometallics by simple nucleophilic substitution, as in this example. Here, triethyl magnesium bromide reacted with THF within 24 hours at room temperature and gave a mixture of mostly the substitution product and a small amount of triphenylmethane. Let's check some further potential side reactions. I already showed you the product mixture resulting from adding a strong base to cycloheptene oxide. Also, non-bicyclic epoxides can yield cyclopropanes as byproducts, as in this example. However, the main product was a secondary allylic alcohol formed by cleavage of the tertiary CO bond. In this instance, the choice of solvent had a strong impact on the selectivity. With the polar solvent HMPA, mainly a cyclopropane and a small amount of a tertiary allylic alcohol resulted. Thus, it is certainly worthwhile to try a few different solvents and bases if one's reaction does not yield the expected product. Another potential side reaction is the alkylation of the base. In this example, a terminal epoxide was treated with one equivalent of aluminum isopropoxide, and a useless mixture of mostly ethers resulted. With an internal epoxide, the yield of allylic alcohols was a bit higher, but still a lot of ether was formed. Some reagents can bring about a clean isomerization of epoxides to aldehydes or ketones. As I showed you earlier, cyclooctene oxide can be converted into an allylic alcohol with lithium phosphate or potassium terzbutoxide, but with sodium iodide the main product was cyclooctanone. Here are some more references which you can also find in the description of this video. Under the Community tab there's a PDF version for subscribers. The next presentation of this video playlist is about the preparation of alkenes by substitution of vinylic hydrogen. There you can find examples of cationic, radical and anionic oligomerizations, as well as Friedel-Crafts acylations and Heck reactions. See you!